Hello and welcome to my science tutorials. In today's video, we want to look at series resonance, where we'll be talking about resonant frequency. Before we begin, if you're new to my science tutorials, kindly consider subscribing and turning on the notification button so that you will stay updated of any of our latest tutorial that we'll upload in the future. So without further delay, let's begin. Now, in our previous tutorial, we did mention or we talked extensively about RLC, series AC circuit, where we said this is just a circuit having a resistor, an inductor, and then a capacitor connected in series. Now, when we were looking at this resistor, inductor, capacitor circuit, we came to a point where we were talking about capacitive reactance and then inductive reactance. We said that there are three things that can happen. The first one is we can have our capacitive inductance to be greater than the inductive reactance. The second one is when we flip this guy, so we can have our inductive reactance being greater than the capacitive reactance. Now, the third phenomenon that can happen is when we have our inductive reactance to be equal to the capacitive reactance. And when we have this phenomenon occurring, we describe this phenomenon as resonant series resonance. So this is where series resonance occurs. So in the point where we have an RLC series circuit where the capacitive inductance is equal to the inductive reactance, we said at that point we have something we call series resonant, and the frequency at which these two guys are equal is what we are calling the resonant frequency. Now, at this series resonance, there are a couple of things that happen. At series resonance we realize that the inductive voltage will be equal to the capacitive voltage. That is one of the things that happens. Secondly, we realize that the impedance of the circuit is equal to the resistance in the circuit. And then from there, we realize that instead of using V is equal to IZ, which we normally use in an RLC series circuit, we can also use, or this is equal to V is equal to IR, just using the resistance of the resistor in that particular circuit. So it means that this guy and this guy are in phase, so they cancel each other out, and then just the resistance in that particular RLC series circuit becomes the only opposition to the flow of current. So your impedance will be equal to your resistance, as we stated over here. Now, because we are having our capacitive reactance to be equal to the inductive reactance, let's look at what happens. So when XL is equal to XC, we know that mathematically XL is given to us as 2 pi FL, and this is equal to our capacitive reactance is equal to 1 over 2 pi FC. Now, the frequency at which the inductive reactance is equal to the capacitive reactance is what we are calling the resonant frequency. So we are representing the frequency over here by FR. So let's try to make the frequency the subject. So if we cross multiply over here, we are going to get 4 pi squared resonant frequency squared LC, that is this multiplied by this, is equal to 1. Now, because we want to make resonant frequency the subject, we divide both sides by 4 pi squared LC over here to by 4 pi squared LC. So we have resonant frequency squared to be equal to 1 over 4 pi squared LC. Now, to get rid of the square sign which is attached to the resonance frequency, we bring a square root and then a square root over here. So this cancels this. So we have the resonant frequency to be equal to the square root of 1 is still 1. So we have 1 over the square root of 4 pi squared, okay, is equal to 2 pi, because 4 here is 2 squared, pi squared is also pi squared, so we apply the root sign, it will be 2 pi. Then the only thing that will be left is just the root sign being applied to the inductance and then the capacitor. So this is what we get as our resonant frequency. So our FR over here is what we are calling the resonant frequency. The resonant frequency. We know that our L is our inductance of the inductor. Our C is the capacitance of the capacitor. All right. Also, in this series resonance circuit, we often describe the circuit as an acceptor circuit, since it is at this point that the minimum impedance occurs and then the maximum current is also given out. So at resonant frequency, the resistance to the flow of current is at the minimum. Because it's at the minimum, the current experienced at this point is at the maximum. It's at the maximum over here. So the keynote over here is that when we have an RLC series circuit and then we have this third condition being met, where we have the inductive reactance being equal to the capacitive reactance, we say that that phenomenon is called series resonance, and then the frequency at which it happens is what we are calling the resonance frequency, and that is given mathematically as 1 over 2 pi the root of LC, as we can see over here. So let's go ahead and look at some questions to see how we apply or we use resonance frequency in calculation. Okay, so we have example number 1. A coil of resistance 10 ohms and an inductance of 125 millihenry is connected in series with a 60 microfarad capacitor across a 120 volt supply. At what frequency does the resonance occur? Find the current flowing at that resonant frequency. Very good. So this is very easy for us to do, straightforward and pretty easy. So let's write down our solution. Now the first thing we need to note is to write down our parameters to see what we have, what we don't have, and then how we can proceed forward. So we have a coil having a resistance of 10 ohms. So we have our resistance is 10 ohms. And then we were told that the inductance L is 125 millihenry, and then it's connected in series with a capacitor of capacitance 60 microfarad across a voltage of 120 volt supply. We're asked that at what frequency, or the resonance frequency, does this occur, and we also to find the current at which this occurs. All right, this is pretty easy, pretty straightforward. We stated the fact that at resonant frequency XL is equal to XC, where we went ahead and found out that the resonant frequency FR is equal to 1 over 2 pi the root of LC. So from here we can go ahead and find our resonant frequency to be equal to 1 over 2 pi root. The L, which is the inductance given to us over here, is 125 times 10 raised to the power negative 3 multiplied by, we have our capacitor having 60 times 10 raised to the power minus 6 over here as the capacitance over here. So our resonance frequency is equal to 1 over 2 pi the root of 125 times 10 raised to the power minus 3 multiplied by 60 times 10 raised to the power minus 6 will give us a frequency of 58.12 hertz. Okay, so the 58.12 hertz is now the frequency at which the resonance frequency at which the resonance is occurring. So this is our resonant frequency. Now we also to find the current at which the resonance frequency occur. Now ideally we have to use V is equal to IZ. That means we need to find the impedance of the entire circuit using the capacitor, the inductance, finding the inductive reactance and then the capacitive reactance, and then using the formula Z is equal to the root of R squared plus into bracket XL minus XC squared. But remember, I said that as at resonant frequency, I said that XL is equal to XC over here. And when that happens, we realize that our impedance is equal to the resistance in this entire circuit. So that means that we don't need to find the impedance, as the impedance is equal to the resistance. So it means we can use voltage is equal to IR, and we can use that to find our current. Now we're told that the resistance in this particular circuit is 10 ohms, and we're given the voltage to be 120 volts. So we have 120 is equal to our current is still here, I, multiplied by the resistance is over here is 10. So if we divide both sides by 10 and we cancel that out, we have our current to be equal to 120 on 10 will give us 12 amperes as our current over here. Alright, so let's have a look at the second example. We have the current at resonance in a series RC LCR circuit is 100 microamperes. If the applied voltage is 2 millivolts at frequency of 200,000 hertz and the circuit inductance is 50 microhenry, we have to find the circuit resistance and then the circuit capacitance. Alright, so let's go ahead and look at all the parameters that we have in this particular question. So we write down our solution. We're told that the current in this particular circuit is 100 microamperes. So 100 times 10 raised to the power minus 6 amperes. And then we're told that the voltage V is equal to 2 times 10 raised to the power minus 3 volts. The frequency, which is the resonant frequency, is 200,000 hertz. And then we're also told that the circuit inductance, which is L, is equal to 50 microhenry. We have to find the circuit resistance and the circuit capacitance. Alright, so let's go ahead and look at what we can do. Now, for us to find the circuit resistance, we know that voltage V is equal to IR when we have resonant frequency occurring. So we have the voltage, we have the current, we can easily find our circuit resistance. So our voltage here is 2 times 10 raised to the power minus 3 is equal to our current here is 100 times 10 raised to the power minus 6 multiplied by our resistance R. So if we divide both sides by 100 times 10 raised to the power minus 6, we can get our resistance R to be equal to 2 times 10 raised to the power minus 3 on 100 times 10 raised to the power negative 6 is going to give me 20 ohms as my resistance. So my resistance in this case is 20 ohms. Alright, so now let's go ahead and find the circuit capacitance. Now, for us to find the circuit capacitance, we know that the resonant frequency FR is equal to 1 over 2 pi the root of LC. Okay, so we need to make C the subject over here. So we need to do a little bit of change of subject. So if we cross multiply here, we realize that we have resonant frequency multiplied by 2 pi the root of LC will give us 1. So we divide both sides by resonant frequency multiplied by 2 pi. Resonant frequency multiplied by 2 pi. We will be left with the root of LC is equal to 1 over resonant frequency 2 pi. So we square both sides to get rid of the root sign. So we have LC is equal to 1. Okay, so we squared both sides. So 1 squared is still 1 over resonant frequency squared 4 pi squared. That is if we square both sides. So that implies that our LC is equal to 1 over 4 pi squared resonant frequency squared. Okay, so we can divide both sides by L for us to get our C. So if we divide both sides by L, our C will be now be equal to 1 over, if we do this computation very well, we are going to get 1 over 4 pi squared resonant frequency squared. This is divided by L, okay, so it will be multiplied by 1 over L. So we have the L will now come at the denominator over here. So we can go ahead and find our capacitance, and this will be equal to 1 over 4 pi squared. Our resonant frequency we were given is 200 times 10 raised to the power 3 squared. Don't forget that. And then our inductance is 50 times 10 raised to the power minus 6. Okay, so if we do that and we compute that, we realize that 1 over 4 pi squared multiplied by the resonant frequency squared multiplied by the inductance is going to give us a capacitance, or our C will be equal to 1.267 times 10 raised to the power minus 8, which we can rewrite as C to be equal to 12.67 nanofarad. So this is now our circuit capacitance. Right, so let's go ahead and have a look at one final example. So the last example in this tutorial, I want to find the resonant frequency of a series AC circuit consisting of a coil of resistance 10 ohms and inductance 50 microhenry and capacitance 0.05 microfarad. Find also the current flowing at resonance if the supply voltage is 100 volts. This is also very easy. So let's write down our solution. As usual, let's write down all the parameters that we have to see what we are lacking and where to go from there. So we're asked to find the resonant frequency FR, so we do not know that. And then we're told that the resistance, okay, a coil having a resistance of 10 ohms, and then an inductance L of 50 millihenry, and a capacitance C is equal to 0.05 microfarad. And we're also, the question is also asking for us to find the current. Okay, we don't know the current flowing at resonance if the voltage supply is 100 volt. All right, so this is very easy. So the first thing we have to do is to find the resonant frequency. We know that resonant frequency is equal to 1 over 2 pi the root of LC. We have L, we have C, we know 2 pi, so it's easy for us. So resonant frequency is equal to 1 over 2 pi the root of, our L over here is 50 times 10 raised to the power minus 3 multiplied by our capacitance C is 0.05 times 10 raised to the power minus 6. Okay, so if we compute everything we have over here into our calculator, we are going to get 3.183 kilohertz as our resonance frequency. All right, so the second part of the question is demanding we find the current if the supply voltage is 100 volts. So over here we were told that V is equal to IR, and then we already know our voltage, that V is equal to 100 volts. We know our resistance to be 10 ohms, and then we don't know what our current is. So if we make the current the subject from here, we are going to get current will be equal to the voltage on the resistance, and this will be equal to the voltage here is 100 volts divided by the resistance. The resistance over here is 10, and so if we do that calculation, this will cancel this, and then 10 divided by 1 is 10. So we are going to get 10 amperes as our current in this particular example. So thank you so much for watching. This is the end of series resonant and how to calculate the resonant frequency. Up next, we'll be looking at how to calculate something we call the Q factor, and then we'll also be looking at a combination of Q factor and then resonant frequency as a question altogether and see how we can solve them. So thank you once again for watching, and I will see you in the next video. Bye bye.